You know, when we think about making AI smarter, our minds usually jump straight to the model itself, right? That huge neural network, the brain. But what if the biggest performance gains aren't in the brain at all, but in the code that surrounds it? Okay, let's just start with a question that sounds kind of impossible. How in the world do you make an AI a staggering 6 times better without ever touching the model itself?
Well, the answer comes from this fascinating paper by a team at Stanford, MIT, and Crafton. And they put it perfectly. The code that determines what to store, retrieve, and show to the model often matters as much as the model itself. They're talking about something called the LLM harness.
So let's really dig into this idea of the harness. It's what the paper calls the hidden performance knob, and for good reason.
So what exactly is an LLM harness? Well, put simply, it's all the code that wraps around a large language model. It's the system that manages all the information the AI sees, what it remembers, and what it pulls up from that memory to solve a problem. Think of it like the AI's personal assistant, its memory manager, and its librarian, all rolled into one.
This visual here is a great way to picture it. If the AI model is the brain right there in the center, the harness is all that code scaffolding around it. It's not the brain itself, but it's the structure that tells the brain how to work efficiently on whatever task you give it.
Okay, so if this harness is so important, how do we make it better? Well, that brings us to the old way of doing things, which we could probably call optimizing with amnesia.
See, the core problem has always been that designing these harnesses is this slow, painstaking manual process. It's all been based on human intuition and a whole lot of trial and error. Developers would look at a failure, tweak some code, and pretty much just hope for the best.
And this is where that amnesia idea really comes into focus. Think of the old automated optimizers like a detective trying to solve a crime, but with total amnesia. They're memoryless. They get a simple pass or fail score, maybe a really short, compressed summary, but they have no idea why something failed. Now, the ideal optimizer, that's a detective with a perfect memory. It sees the full source code, every single detail of the investigation, and it understands exactly where things went wrong and why.
And the paper just nails this problem perfectly with this quote. Compressed feedback often removes the information needed to trace downstream failures to earlier harness decisions. Basically, by summarizing the results, you're throwing away the very clues you need to actually solve the case.
So how do you solve this? Well, you give the detective its memory back. And that leads us to the core breakthrough here, building a system that acts like a detective with a perfect memory.
This is the big idea behind MetaHarness, and it's not some ridiculously complicated new algorithm. It's actually a beautifully simple and powerful concept. Give the AI optimizer access to everything. The full source code of every past attempt, all the performance logs, every single execution trace, and just store it all in a simple file system.
So the process works in this really simple, powerful loop. First, an AI agent acts as our detective, and it inspects the entire case file of every past attempt. It actually uses another powerful LLM to analyze all that code and all those logs to spot failure patterns. Then it literally rewrites the harness code to try and fix them. Second, that new harness design gets tested. And third, and this is the crucial part, a new, super detailed file with the code, the traces, and the score is added to the history. It's this perfect feedback loop that builds an ever-growing memory of what works, what doesn't, and most importantly, why.
Okay, so the theory is super elegant, love it. But does it actually work? Let's get to the fun part. The results are in.
First up, online text classification. On the left, you got ACE, a state-of-the-art system that was designed by hand. In the middle, an older optimizer. And way over on the right, that's MetaHarness, just blowing past both of them, with a final accuracy of 56.7%. That is a massive 7.7-point improvement over the best hand-tuned system. And get this, it did that while using 4 times fewer context tokens. So it's not just better, it's way, way more efficient.
I mean, this says it all, right? The paper states it's 10 times faster and converges to a better harness than the old automated methods. It gets to a better answer, and it gets there in a fraction of the time. It's a total game changer.
All right, but does it work on other stuff? Is it a one-trick pony? Let's pivot to something completely different, agentic coding. This is a super competitive benchmark called Terminal Bench 2. And yep, there it is again. You see MetaHarness coming out on top at 37.6%, finding a harness that outperforms the best hand-engineered systems. And just to put that into perspective for you, MetaHarness automatically discovered a harness that now ranks #1
#1 among all agents using that same base model on the public leaderboard. It didn't just beat a baseline, it went out and took the top spot.
Okay, and for our third domain, let's look at something incredibly difficult. International Math Olympiad level problems. Here, the harness discovered by Meta Harness delivered an average improvement of 4.7 points. That is a significant jump on problems that stump even the most powerful AI models out there.
And this might be the most impressive part of all, the transferability. The harness was discovered using just one model, but that exact same harness improved performance across 5 completely different AI models that it had never even seen before. This proves it's not some brittle, over-optimized solution. It's a genuinely robust strategy that works everywhere.
So these results are pretty amazing. But let's zoom out for a second and just think about what this really means for the future of how we build with AI.
When you really put it all together, the advantages are just crystal clear. The harnesses it finds, they generalize to new datasets. They transfer across different models. The whole process is incredibly efficient. We're talking hours, not weeks. And maybe most importantly, the result isn't some black box we can't understand. It's inspectable, readable code that a human can actually look at and learn from.
This work highlights a powerful and recurring pattern we see over and over in technology. Once you make a search space accessible, in this case, the space of all possible code for these harnesses, strong general-purpose AI agents can often outperform specialized, hand-engineered solutions. It really is a fundamental shift in how we build these complex systems.
And that leaves us with a final thought to chew on. We've just seen a system that automates the code around the AI, and it leads to these massive gains in performance. So the real question is, if we can automate this layer, what is the next frontier of automation we can unlock?